Hi everyone, I am Ananya Nambyar from RI Mysore, currently pursuing my MSc in Physics degree. Today we'll be discussing about the building blocks of liquid crystals. Most of us were taught that there are generally three phases of matter, namely the solid, liquid, and the gas. But did you know that there are also intermediate phases called the liquid crystals? At certain temperatures, some material become liquid crystalline. We shall start by seeing what are liquid crystals and their classification. The classification of liquid crystals are done into two, namely the thermotropic and lyotropic. Lyotropic crystalline phases are seen in living systems such as protein, whereas the thermotropic phases occur in certain temperature range. Thermotropic indicates that the system is temperature dependent and lyotropic indicates that the system is concentration dependent. Further, on basis of thermotropic, the system is divided into three, namely the cholesteric, smectic, and nematic phases. Cholesteric phases are used in thermometers and other displays, and smectic phases are soap-like and nematic phases are used in cell phone and calculators, etc. Liquid crystals, as we know, are of two types, thermotropic and lyotropic. In thermotropic, we have high molar mass systems and low molar mass systems. The high molar mass system, which is the polymers, have two types, that is the main chain polymers as well as the side chain polymers. And low molar mass system are made up of mesogens, which are rod-like and disc-like. The shape is what gives it some degree of order. Example, if we have a rod-like structure, a long axis in a molecule, this is something that is relatively rigid, and so these kind of molecules line up against each other. Similarly, if we have a flat or planar molecule as shown, it will make something that looks like a disc which stack upon each other to give us the liquid crystal. Building blocks of liquid crystal. They are small elongated molecules, small discoid molecules, the long helical rods, the polymers, as well as the associated structure. We can see how each of these help in building the liquid crystal. To begin with, we go with the small elongated organic molecules. They are organic molecules which have rigid rod-like structure as seen in the picture. The liquid crystals thus created are called Calamite liquid crystal. The structure as we see here, they can be either two para-substituted atomic rings connected to the functional group, which are tails, or one para-substituted aromatic ring and one para-substituted cyclohexane, which is further connected to the tails, that is R and R dash in the figure given here, which are usually alkyl or alkoxy chains. The long tail stabilizes lamellar arrangement, and if both the tails are of same length, we get the nematic phases. The relative efficiency of nematic phases depends on certain ranking of the group, that is, the R and R dash functional groups depend on the efficiency of nematic phases. The most common example is PAA, that is p-ethoxyanisole. Here you see two benzene rings and they are connected and both sides you have tails. It's called a nematogen, that is, they give rise to nematic type mesophase in a particular temperature. For PAA, it is a range of 116 degrees Celsius to 135 degrees Celsius at atmospheric pressure. Another example that is most commonly used is MBBA, that is the N-methoxybenzaldehyde p-butylaniline. Here also we can see two rings that are connected and have a tail. It is also a nematogen that is used in laboratory to demonstrate the liquid crystal experiments. This gives its nematic liquid crystal phase between 20 degree to 47 degrees Celsius, but it is less stable than PAA, which is a drawback. Next is the small discoid molecules. These molecules form a columnar phase. Hexasubstituted phenyl esters is the simplest example of such a system. They have rigid core of different symmetries which may not be necessarily planar, a number of aliphatic chains attached to the core with suitable linkages. Triphenyline is a thermotropic disc-like nematogen which is the best example of small discoid molecules. The stability of columnar phases requires some amphiolic interactions. The core and chain separates and the chain provides lubrication between the column. The images shown here is the example of how the small discoid molecules look like, and this is the image of the triphenyline, which is a thermotrophic disc-like nematogen. Long helical rods are next kind of systems. The rigid polymers in solvent have rod-like structures with a length of order 300 angstrom and width of 20 angstrom. In concentrated solution, they give mesophases. When we increase the temperature, the individual rods in the solvent are disrupted. We can call these as rod-like liquid substrate. As they cannot vary with temperature, these can be made to transition using their concentration. Hence it is called lyotropic. This shape helps in different orientation of molecules compared to rod-like or disc-like molecules as they give the chirality and asymmetry. The deoxyribose nucleic acids and certain viruses like tobacco mosaic virus shows similar phases. Temperature affects the existence of these rods. The helical structure helps in selective reflection of light. This optical property are made use in the displays and devices that utilizes low energy. Next comes the polymers. Polymers are very stable. Thermotrophic mesomorphism is also observed in these set of systems. We insert the flexible parts in macromolecules and get two classes of polymers. First one is the main chain polymers. This is also known as the backbone polymers. The rigid mesogenic parts are attached with the flexible links. As we said, the system is very stable and thermotrophic mesomorphism is observed. The nature of mesogenic group, flexible spaces and their lengths can be varied to get different main chain polymers. The use of copolymers with different spaces and mesogenic group changing the degree of polymerization etc. also helps in doing the same. Design and synthesis of such polymers are difficult as they have high melting point and rigidity. Processing to decide shape is difficult. As shown in the figure, we have the backbone polymers which are attached with the flexible links. Next set is the side chain polymers. The side chain polymers, here the mesogenic groups are connected through flexible spaces, mostly like alkaline chains. And the examples are polysiloxanes, polyacrylides, etc. For main chain polymers, we have examples which is polyester amide and polyaryl ether ketone, polyester amide. These are the figures of polyesteramide, polyaryl ethyl ketone, and polysiloxanes, which are examples of side chain and main chain polymers. Associated structures. A typical example is the soap water system. In such system, there is an aliphatic ion and positive ion where polar head of acid tend to be in close contact with water while a polar aliphatic chain avoids water. This condition is to be satisfied in an amphiphilic system, but these opposite conditions cannot be satisfied by a single molecule, but it can be satisfied by a group of molecules. Same building blocks can give smectics, nematics, as well as columnar faces, which is the advantage over the simple molecules which can result in any one, that is either smectics and nematics or nematics and columnar faces. The block copolymers are the best example of these associated structures. So we have seen the different building blocks of liquid crystals. To summarize, we have found four types of building blocks. The first one, small organic molecules, that is either rod-like or disc-like, for which an amphiphilic character may or may not be crucial. They are commonly designated as thermotrophic. The rods in liquid structure, that is the long helical rods. Here the temperature effects are difficult to control and natural parameter which we can adjust to induce a phase transition is the concentration of rod, by which it is called pleiotropic. Next is the polymers, which had main chain or side chain polymers. They were thermotropic mesogens. Aside from temperature, the molecular weight may also be considered as a variable. The last one was the associated structure, that is the amphiphilic compounds. These may give rise to association and to mesomorphic behavior, either in the presence of a selective solvent or as a pure phase. Thus, depending upon which of the above conditions hold, amphiphilic compounds may be lyotropic or thermotropic. Thank you.